Hello, everyone. Thank you for coming to my tutorial on incentive-aware machine learning. I'm Harapali Mata, and I'm currently a postdoc at UC Berkeley. And starting from June of this year, I'm going to be an assistant professor at MIT. So I'm sure most of you in this audience know that machine learning algorithms for decision making are almost everywhere nowadays. For example, a machine learning algorithm may decide whether you qualify for a loan or not, whether we will get probation, whether after an interview with a video interview software, we will be invited for an on-site interview and ultimately be given the job of our dreams, and whether students who are applying to college will be admitted to the colleges of their choice. Now, because of the fact that these decisions are really consequential for people's lives, people oftentimes try to change the data that they feed into the algorithms that will make these decisions. So, for example, people may try to increase the number of credit cards that they have, or increase the number of bank accounts, or improve their credit history right before applying for a new loan. Students may try to improve their GPA in various ways, retake the GRE, or even pay for tutoring classes and change schools in order to obtain a better in-class ranking. And similar examples of strategizing can be viewed also in the video interview software case, where people may try to dress a certain way, they may try to hide piercings or tattoos, and even change the way that they talk. So what is the problem here, and what is a general problem that this area is trying to deal with? The problem is that if machine learning algorithms ignore this strategic behavior, this adaptation from the side of individuals, we risk making policy decisions that are completely incompatible with the original policy's goal. And I'd like to zoom in a little bit more and talk to you about what exactly can go wrong from the standard machine learning pipeline when agents strategically adapt to the decisions that we output. So to showcase what can go wrong, I'd like to remind everyone here that the reason why policymakers and mechanism designers originally thought that machine learning was the correct thing to use for decision making is that we really wanted to leverage human data and create better decisions. And the reason why machine learning was deemed appropriate lies at the very heart of the machine learning paradigm, which says that if you're given access only to a training data set, then patterns that you identify in the training data set directly translate to patterns in the test data set, which is what you want to evaluate your rules, your algorithms on. And to make this more concrete, this means that if given access only to a training data set, you create a classifier that is good for the training data set, then you can deploy the same classifier for the test data, the unknown data. And by standard guarantees of machine learning algorithms, if you had accuracy in the training data set, this translates to approximate accuracy in the test data set too. Now, the problem is that when we use these systems to make consequential decisions for people's lives, the data corresponds to individuals. They are not static. And these individuals have agency, and they want to affect the decisions that are made on them by the machine learning algorithms. So take, for example, the school process, the school admission process that we had on the previous slide. Now, each data point corresponds to a student's features. These features can be the SAT score, the GPA, the class ranking, and so on and so forth. And so the classifier decides whether a student is essentially qualified to be part of the school or not. But for students, for candidates that are very, very close to the boundary, then they know that by changing their data slightly, by retaking the GRE, by super optimizing in certain directions, then they can jump the classifier and ultimately be admitted to the school. This means that the training decisions that we make affect the test data that we will see. And so what should the institution, what should machine learning do in this case? Well, machine learning should adapt to the behavior of the agents. And this is at the heart of what incentive-aware machine learning does. Now, every time that you hear someone talking about incentive-aware machine learning, I'd like you to keep in mind that there are three key stakeholders that we care about. The first stakeholder is the institution. These are algorithm mechanism designers that sit at banks, schools, firms, the justice system. They're going to create learning tasks for accurate prediction in an effort to either increase profit or have more just decisions, and so on and so forth. The second stakeholder is the individual. These are the people, the data providers, who will supply their data so that decisions are made on them by the algorithms of the institutions. The actions that people take is to strategically change their data within their power, and their goal in doing so is to get the best outcomes for them. So in the loan approvals case, for example, a person may try to increase the number of bank accounts that they have or the number of credit cards so that they are deemed more creditworthy by the algorithm. And the final stakeholder is society. Society is comprised by all people and institutions as a whole. Society's actions are fairly broad. We can regulate, we can create public pressure, we can create norms and expectations about the algorithms that the institutions can use. And society's goals are also fairly broad. We strive for fairness, we strive for robustness to bad actors, and an increase in the social welfare of the population. So what are the goals of this tutorial, and what do I hope that you get out of it after this 2 hours of material? So the first goal is that I want you to understand what exactly is incentive-aware machine learning and how it is different from distribution shift or adversarial machine learning, which is a more traditional viewpoint of what happens when machine learning algorithms interact with humans in the wild. The second goal is that I want you to understand the different perspectives that researchers have taken in the incentive-aware machine learning literature and the ways in which they approach the problems from the perspectives of the different stakeholders that I mentioned earlier. And then the third goal is to give you an introduction to the main results and techniques that have been used in this area so far. So I'd like to give you an idea of how this tutorial will be run. It's split into two parts. In the first part, we just concluded with the introduction of what is this area and why it's important. Then I'm going to give you some basics for algorithmic game theory, and then study strategic classification, which is one of the very prominent examples of incentive-aware machine learning as a stackable game. Then we're going to contrast strategic classification with distribution shift and talk about the performative prediction perspective. And I will conclude this part by a bird's eye view of the different perspectives in the literature. Then we're going to have a short break that is going to be 5 minutes. Feel free to stick around and ask questions, or you can just join after 5 minutes. And then in the second part, we will talk about the robustness, the fairness, and the improvement perspectives. We will conclude with some open directions. Then we will have a 10-minute Q&A, and then we have an amazing panel that will discuss more about the area of incentive-aware machine learning. Now, for technical purposes, I have Rocket Chat here open. I'll try to monitor it, but if you see that I'm not very much on top of it, it's because I want to get done with the material, and then I'll address the questions that we have in the Rocket Chat. Okay, so without further ado, let me jump into giving some background on game theory notions that will be very useful throughout this tutorial. So some mechanism design basics. I'm going to define in this slide what is a mechanism. So in these types of problems, we have n agents. These agents are competing with each other. Each of the agents has a true type, the actual type, which corresponds to how much she values the alternatives that are presented to her. And she also has a declared type. And this type is what the agent lets us know about their type. This declared type is due to the fact that we don't assume knowledge of the actual types usually. And we allow the agents to declare the types that they want. There's a set of alternatives, and these are going to be denoted by script AI. And the set of alternatives for agents apart from I is script A minus I. And a quantity that's going to be very important is I's utility when playing Xi, which is basically the raw column here in script AI, when other players play X minus I. So what is a mechanism? A mechanism should be thought of as a black box or an algorithm that takes as input the declared types, the alternatives, and the utilities of the different agents, and outputs an outcome for each agent. And to make this slightly less abstract, I'm going to talk specifically about games. What is a game? A game is a modeling tool for social situations among competing agents. For example, you should think of politicians deciding on their messages for the election. In this example, we have two players, two agents. One is politician one, the other one is politician two. And they want to decide between how to allocate their time on the topics of economy and society and the topics of morality and tax cuts. Now, the solution concept that we care about when it comes to games is called the Nash equilibrium. What is the Nash equilibrium? The Nash equilibrium is a mixed strategy X star for all of the agents, where the utility that each agent gets for playing XI star, given that all the other agents are playing according to the Nash equilibrium, is always larger than the utility that this agent would have gotten if all the other agents were still playing the Nash equilibrium, but player I deviated to something else. So what does that mean? If you do the calculations here, you'll see that the Nash equilibrium for player one is to play the economy card with 3/7 probability, and the society card with 4/7. And for politician two, the Nash equilibrium is for them to play the morality card for 2/7 and 5/7 the tax cuts. This is a way that tells us how basically the politicians should allocate their time based on the utilities that they get and how the other politician will allocate their time so that they converge to a Nash equilibrium. Now, I'd like to point out that the game that I have here is not a random game. It's known as a zero-sum game. Zero-sum games are games where the gains of one of the agents are equal to the losses of the other agent for each of the alternatives. And this is important because in zero-sum games, any of the players can move first and the other can best respond. So basically, there's this exchangeability of play. No agent wins anything by going first. That is not true, however, in every game. And specifically, I wanted to introduce to you Stackelberg games, which are going to be extremely important for the rest of this tutorial. So what changes in Stackelberg games is that the players are now principal or leader and a follower. We call the first player a principal because they have commitment power, which means that they go first and they announce with what probabilities they're going to play each of the alternatives that they have. So for example, here, politician one comes out and says that, hey, I'm going to play my economy card for half of the time and the society card for half of the time. And then the follower best responds according to what the principal committed to. So what is the solution concept that we care about in these types of Stackelberg games? The solution concept is known as the Stackelberg equilibrium, and it's a mixed strategy for the leader. We say that a mixed strategy is a Stackelberg equilibrium, the utility that the leader or the principal gets for playing this mixed strategy, if the agents are going to best respond to it, is larger than the utility that the principal gets if they played any other strategy, and the agents best responded to this other strategy. And if you do the calculations here, you can conclude again that the Stackelberg equilibrium, when the principal goes first and the follower follows, is exactly the same as the equilibrium that I showed on the previous slide. And this is not random. This is because in zero-sum games, the Stackelberg and the Nash equilibrium coincide. But this is not true for general games. So again, just a very brief summary. Why is Stackelberg equilibrium different than Nash equilibrium? First, we have commitment power, which we didn't have it in Nash equilibrium. And second, it is defined on the leader space. The agent space, the follower space is assumed to always best respond. So why did I introduce Stackelberg games in this incentive-aware machine learning tutorial? The reason is that in one of the very first papers in this area, the wonderful paper of Hart, Megiddo, Papadimitriou, and Wooters, strategic classification in the offline world was modeled as a Stackelberg game. So again, what are the agents? What are the players that we have in this game? We have on the one hand an institution who, for example, can be a bank, who wants to take actions like a linear classifier, and the goal is to give loans to credit-worthy people. And then on the other hand, we have an individual. These are people applying for loans. They can strategically change their features before they apply, and their goal is to be granted loans. These are the two players that I'm going to have in my game. And the institution is going to be the one who has commitment power. So they are our principal here. So how does this game progress? In the beginning, nature draws the agent's features. These can be the credit score, demographics, and so on and so forth. I'm going to denote this by X, and it comes from a script X feature vector space from a distribution script D. Now, the learner, without observing X directly, commits to a classifier alpha from the features to -1, 1. It's a binary classifier. The agent observes this classifier and the features and decides in some way that I'm going to define shortly to report a potentially altered feature vector delta X. The learner gets to observe the true label of the point, where h of x is the ground truth classifier, and ultimately they collect utility, which is equal to the probability of classifying this person correctly, even after the person strategized in the feature that they sent to you. Now, I'd like to pause here because if this is your first time seeing strategic classification, it may be a bit dense and a bit weird. So I'd like to break some things down. The first thing that I want to clarify is what is different from standard classification here. In standard classification, we usually assume that our machine learning algorithm has access to the data distribution, to the data that are produced by the data generating process. So you see the pairs X, Y, okay? Now, what happens in strategic classification is that this generation of X, Y is hidden from the learner. Instead, before it is revealed to the learner, there's a middleman. And this middleman decides how to change the X's, the features, which is what the learner ultimately gets to see. And to put these things that we have here more into the context of the example that we have here on the right, the original features, as we said, can be the original credit score, the original demographics, the original number of bank accounts the person had. But if the person sees, for example, that the classifier values more an increase in the number of bank accounts that they have, then they may try to increase the number of bank accounts that they have before submitting the features to the loan company. And so I've defined this game, I've defined the two players, but I haven't told you what are the goals and what is each player optimizing for. So the institution, who is the principal here, they have commitment power in that they announce the classifier and subsequently the individual best response. The institution's goal is to achieve the Stackelberg equilibrium classifier. This is the classifier that if it were to be deployed and we allowed the agents to best respond to it, then we would maximize the probability that we classify the agents correctly. So it's the most accurate classifier if you allow the agents to best respond. And what is the individual's goal? Another way of saying what is the individual's goal is to understand how is delta X produced. Can the individual say something that is completely crazy? And the answer is no. In this area, in incentive-aware machine learning, we assume that the individual's response comes from their strategic behavior. This delta X is defined as the maximum X that maximizes the value of the agent for passing the classifier minus the cost that they have for manipulating from their original point X to the reported point X prime. Okay, so summary, the institution strives for a Stackelberg equilibrium classifier. This is the most accurate classifier, and the agents strive to be positively classified, and they strategize with their data. Is it even possible to achieve this Stackelberg equilibrium? Well, in this wonderful paper, Hart et al. Showed that it is possible in polynomial number of samples to learn approximately alpha star by incorporating the strategizing information. Okay, so they showed that if you know in an offline setting how the individual is going to strategize, then you can incorporate this information and in polynomial number of samples, achieve the most accurate classifier. What I want to do next is I want us to focus on the individuals or the agent's strategic behavior and give you some more information about why it is different from standard adversarial models in machine learning and what the connections are with the notion of distribution shift, with which many of you in the audience may already be familiar. So again, as a reminder, what are we doing here? We're assuming that we have an institution. They're going to have a decision-making rule. This is like a classification or regression that according to this decision-making rule, they're going to make policy decisions. And then we have our agents. We have people who have some true features X and some behavioral model. This goes into a black box that I will specify in a second. And then somehow after this black box, people decide to send X hat, a potentially changed feature, to the institution. And this is the features based on which the institution makes recommendations for the policy. So the crucial difference between strategic and adversarial models is exactly what the behavioral model that we assume is. So if the behavioral model is strategic, then the X hat, the data point that the person sends to the institution, comes from a maximization process on the agent's utility. So we don't care about what is going to be inflicted on the institution as a result of our change. What we want to make sure is that whatever we report is giving us the best chance of winning something, of gaining something for our own purpose, for our own gain. So examples of like standard utility functions that have been studied in this area include this maximization of a linear value for passing a classifier minus the L2 norm of moving from X to the manipulated point, or for example, maximizing the binary value of just passing the classifier minus the L2 norm of moving from point X to point X prime. How is this different from the adversarial viewpoint? Well, in the adversarial viewpoint, the person will report X hat that inflicts the highest loss to the institution. So if you're familiar with adversarial examples, for example, if we were adopting the adversarial viewpoint here, we would report X hat that maximizes the loss of the institution within and is within a ball of radius epsilon around our true X. So these are the two different viewpoints. When we talk about full adversarial agents, they just want to destroy, to sabotage the algorithm completely. When we talk about strategic agents, they just want to game the algorithm to gain something out of it. And so what is the connection with distribution shift? Well, in both cases, if the institution does not account for the adaptation from the side of the agents, be it strategic adaptation or adversarial adaptation, then we end up having a distribution shift that we haven't taken into account. And I'm going to pause very briefly because there are some questions on the Rocket Chat. The talk slides, yes, they will be shared on the website, my website. A Stackelberg equilibrium does not mean global optimum for the institution, right? It is in fact a global optimum once you allow the agents to best respond. And then there's a question about mechanisms, stems from auction theory. Could the definition of mechanism apply to more general machine learning and decision-making scenarios, such as recommendation systems? The answer is yes. And if you're interested more in this type of modeling, I'd recommend that you check the papers from Economics and Computation, which is the premier conference in this area, and I'm sure there are many works that study this problem. Okay, so picking up from where I left off, I was telling you about distribution shift. So is there a way that we can avoid distribution shift if the agents are strategic in the full machine learning pipeline, where we do not know exactly the utilities of the agents? This is the question that was studied under the name of performative prediction by Perdomo, Zernich, Mendler, Donner, and Hart, this paper at ICML 2020. So what does performative prediction mean? Performative prediction is a prediction that causes change in the target variable. So how is this different from the Stackelberg viewpoint of the game that I introduced earlier? Well, in this paper, the change does not have to be a result of best responding to a linear, structured continuous function. It can be arbitrary, basically. So whenever we talk about prediction that changes that causes changes in the target variable, the question that may come to mind is, especially if we come from a machine learning background, and we don't want to like scrape everything that we have in favor of like creating new algorithms, is can we just avoid performative effects by retraining our algorithms? And to answer these questions, I'm going to focus on two important performance notions that this paper focused on. The first performance notion is known as performative optimality, and the second performance notion is known as performative stability. A performatively optimal model is one that minimizes the expected error of the model, given that the agent's data best responds, not just best responds, but responds to the model. This means that the data changes the target distribution according to the model that is deployed. And what is a performatively stable model? A performatively stable model minimizes the expected loss on the distribution for the model, the theta PS, the performatively stable, that results from deploying theta PS in the first place. So a model that is performatively stable eliminates the need for retraining after deployment, since any retraining procedure would simply return the same model parameters. And if you're familiar with this notion, performatively stable models are essentially fixed points of risk minimization. And if these two notions sound quite familiar at this point, and you're wondering whether they have any connections with the two notions of Nash and Stackelberg equilibrium that we talked about a couple of slides ago, in fact, there are connections with these notions. If we fix the utility of the population, so we fix the way that the population responds to the models that we deploy, that the institution deploys, then the performatively optimal model corresponds to a Stackelberg equilibrium model, and the performatively stable model corresponds to a model that is that leads to the pure Nash equilibrium. So, okay, I've introduced these two performance notions, and this should be quite confusing at this point, okay? Because what should our algorithms optimize for? Should they optimize for performative optimality, or should they optimize for performative stability? Well, addressing one of the questions that we had on the chat, performative optimality, which has connections with the Stackelberg equilibrium, as we talked about in the chat, is the global optimum thing to do. So we should strive to optimize performative. We should try to achieve performative optimality. The problem is that oftentimes it's actually quite hard to do so, and not only that, but in order to achieve the performatively optimal model, we have to scrape all the algorithms that we had before and do everything from the bottom up. So the ideal here would be have the algorithms as you had them, retrain them a couple of times to new data, reach a stable point, and make sure that the stable point is close enough to the performatively optimal point. Now, is this even possible? Well, this paper showed that it is possible under some pretty strong assumptions on the loss function and the way that the distribution changes as a result of the adaptation of the agents. This paper showed that if the loss that the learner cares about is jointly smooth and strongly convex, and also the distribution that is induced by the change in the model is not too sensitive in changes, then you can guarantee that after retraining a few times, you can reach a stable point. The last piece of the puzzle is what are the conditions under which the stable point is close to the performatively optimal point, the global optimum, as we address the question from the chat. Well, the two conditions are that the loss function needs to be Lipschitz and strongly convex, And then you can guarantee that your stable point that you've reached is close to the optimal point. So is everything solved and done? And is my tutorial over after only 30 minutes? The answer is no. For the remaining of this tutorial, what we're going to do is we're going to focus on cases where these assumptions of smoothness and convexity do not always hold. And we're going to focus on trying to optimize directly for the performance of the optimal point or the Stackelberg equilibrium. And we're going to do so from the different perspectives that I'm going to introduce in a second. Now, before I jump into talking about the specific perspectives, there are some questions in the chat that I want to address. In strategic classification, it seems that the learner approximates a classifier under follower strategies. This rests on the assumption that a classifier exists. For example, a separating hyperplane A star exists. Any references on when it doesn't exist, such as regret bounds with respect to the best classifier in hindsight? This is an excellent question, and it's actually a question that I will address in the second part of the tutorial. But let me give you a hint already. So far, notice that I talked about an offline setting. In the second part, we're going to introduce the online setting where this like separating hyperplane A star will not exist. But even in the online setting, I'm going to give you an idea of results that exist in the area about like changing the standard, for example, perceptron algorithm when you have data that are linearly separable. So yeah, it's going to be actually the first section of the second part, so wait for it. Then there's a follow-up in performative prediction. If we assume the agent response is best counter strategy, then PO policy is PS policy. So remember that you can make the connection between PO policy and PS policy only if you talk about zero-sum games. So if the gain of one person is equal to the loss of the other person. Otherwise, the only thing that you can say in this example that you have there, which is the best I read your message as best response, is to say that the PO is actually the pure Nash equilibrium, and the PO, is the Stackelberg equilibrium, and PS is the pure Nash equilibrium. Okay. Cool. So, okay, let me just take a small step back because I think at this point I've given you a lot of material. What have we seen so far? We have modeled strategic classification as a Stackelberg game. We saw what Stackelberg games are. There is this commitment power and the follower best response. And then we discussed that, when everything is offline and the learner, the institution knows the utility of the agents, the learner can exactly design with polynomial number of queries how to learn the optimal alpha star, how to learn this like Stackelberg equilibrium. Then we understood why this is different than like standard adversarial machine learning. We talked about what changes when agents think about strategizing instead of just being adversarial with respect to the rule of the classifier. And then we addressed ways that you can avoid distribution shift whenever your loss functions are smooth and the distribution that is induced by the change, by the adaptation of the agents is not changing too much. And we made the connection between stability and how you can achieve stability by retraining under these assumptions on the loss function, and how this essentially leads to optimality for the institution's accuracy. So what I want to do next is to give you a bird's eye view of the different perspectives in the literature. And I'm going to do so by creating an axis where I'm going to try to put all the important pieces of how to like break down the works in this area. So the first axis, in my view, is the population strategic behavior. For example, is your population of agents homogeneous? Do the agents have the same utility, the same value for crossing the threshold, the same cost for manipulation? Or do we have a heterogeneous population where people have different values for passing the classifier, and also they have different manipulation power? What is this utility function, and do we approximately or absolutely maximize it? Do we talk about a utility function that is defined as maximizing value given the constraints, or is it like value minus constraints? The second axis here is the institution's transparency. Examples of this include whether the rule that we deploy or the algorithm is fully revealed to the agents or partially revealed, whether the rule is like noisy or whether it's randomized. And the final thing is the objective that we care about. So for example, do we care about the principle's accuracy? Is the goal of our setting to understand how to prevent gaming from the side of the individuals? Or is our goal fairness, which usually is achieved through equalizing treatment or opportunities among groups? A third goal that we may strive for is recourse or improvement, helping people to improve their classification as a result of participating in this setting. And of course, like this literature has seen a huge growth in the past couple of years. And here, of course, I cannot capture all the works, but this is a general viewpoint that helps me understand how to place the works into context. And just a slide, if you want to have in mind if you want to like keep in mind how we classify these works, I like to think of them as 5 categories. The first category is robustness. The second category is fairness. Third category is recourse and incentivizing effort. Fourth category is causality. And the fifth category is performative prediction, which we talked about already. You can screenshot this slide, or I will upload the slides on my website in case you want to take a look. And with that, I have concluded the first part. Let me know if you have some questions. I thought that we would get more questions. That's why I'm a little bit early. But yeah. I will wait because I know that there's approximately a minute delay in the chat. Here's a question. Does automated mechanism design fit in here too? Do you want to say more about how do you define exactly automated mechanism design? This is like fairly broad. Oh, and there's another question. Can you reiterate on the difference to distribution shift? Is it just the point in time when the classifier is specified? Oh, that's a good question. So the difference with distribution shift is that basically, if this adaptation happens from the side of the agents, and this adaptation can either be by like a completely adversarial process or a completely strategic one, then you will end up having a distribution shift because your target distribution has changed as a result of your training process. So distribution shift is something that happens whenever you don't account for the adaptation. If you do account for the adaptation from the side of the agents, then you don't have any distribution shift, at least when it comes to like these types of strategic settings. Could you speak a little bit more on the causality connection as well? The answer is yes. This is the third section of the second part. We're going to have more details on that. What work exists with heterogeneous populations? So this is a good question. So whenever we talk about heterogeneous populations, usually what we care about is the fairness perspective here. And this is the second section of the second part, which is coming up. And basically what we care about for heterogeneous populations is to make sure that, when people have different costs for manipulation, you can either achieve good accuracy guarantee, you can simultaneously achieve good accuracy guarantees from the institution's perspective, and you also do not make disadvantaged populations clearly worse off. So this is what we're going to see in the second section of the next part. The approaches rest on the assumption that the followers' deviations, for example, costs to change their features, are known. The results you discussed on PO and PS, do they still hold? I have to clarify some things. So I did introduce the offline version of the problem in the strategic classification version of the problem as a Stackelberg game with the assumption that the followers' deviations are known, the utility is known. What we're going to see in this part here, the robustness, is that the newer perspective that researchers have taken here is that you usually don't know exactly how these deviations are formed. You have an idea that they come from a particular utility function, for example, but you don't know how this utility function is structured. And also, when it comes to like performative optimality and performative stability, mostly the results that we have are with respect to changes that are smooth enough. So you don't need to pinpoint exactly how the change happened. It just has to be the case that the change resulted in, like the change was made in a smooth enough way. And actually, one of our panelists, Celestine, has worked extensively on this area. She was among the authors who introduced it. And so we can address this question to her during the panel too. Welcome back, everyone. For the second part of the incentive-aware machine learning tutorial. As a reminder, we're going to discuss the robustness, the fairness, and the improvement perspectives. Then I'm going to talk to you about some of the open research directions in this area. Then we'll have like a 10-minute Q&A, and we will transition to the panel with our wonderful panelists. So before I jump into the second part, there was a question in the Q&A while we were on break, which was the following. Fair to say, without any strong assumptions like convexity, we have to try everything during exploration. Maybe methods from continuous bandits like discretized exploration of policy spaces sounds exponential complexity though. Arvind, you have the correct intuition here. And this is, I'm going to point out specifically which work is closer to this like discretized exploration of the policy spaces that you mentioned here. Okay, but this is going to be at the first section of this part. So where did we leave off? We left off at discussing briefly the different perspectives and how basically you can break down the literature into the robustness, fairness, recourse, causality, and performative prediction. And in this part, I'm going to mostly talk about robustness, fairness, and incentivizing effort. But at the end, I'm going to briefly touch upon the causality perspective as well. So what changes whenever we transition from the offline model of strategic classification, which, as a reminder, in this offline model, and many of you criticize this on Rocket Chat, what changes when we transition into a world where we don't know the utilities of the agents and how they're going to best respond? Well, this is what was studied in the online model of the problem of strategic classification. And as a reminder, we're going to have two players here. One is the institution, who is a bank and deploys linear classification algorithms. And on the other hand, we have the individual. These are people that are applying for loans. They want to be granted the loans, and they will strategically change their features in order to be approved by the algorithms. So we're going to talk about an online model. So the interaction between the institution and the individual is going to happen repeatedly over capital T rounds. At the beginning of each round, nature chooses the agent's features. These can be the SAT score, the class ranking, if we talk about a school admissions process, or like the credit score, the number of bank accounts, and so on and so forth, if we talk about like a banking example. So these agent's features are going to be denoted by XT, and they're going to be D-dimensional. So we have D features for the agent. The learner, who is the institution, picks a classification rule alpha T. This is linear, and it does not depend on XT because XT is not known to the learner at this point. The agent gets to observe the classifier and the data point xt, yt. This is the original features and the label of the features, which nature chose. And the agent decides how to report to the learner a potentially altered feature vector that depends both on the original xt that nature chose and also on the classifier that the learner announced. The learner observes the label yt and incurs classification loss, which depends on the classifier that the learner deployed and the point that the agent best responds. So again, this can be a bit dense. Remember where we started from in the offline model. In the offline model, we said that What changes from standard classification is that we don't have access to the data generating process. We don't have access to what gets spit out from the distribution, but we only have access to something that has already been changed. This is also the same thing here. It's just that the thing that is changed happens over multiple rounds. So at each round, the learner deploys a classification rule. The agents best respond to this, and the learner observes this best response from the agents. So in this offline model, which happens over a sequence of rounds, what does the institution care about? The institution cares about minimizing a notion of regret, which is called the Stackelberg regret, and is defined as the cumulative loss of the actions that the institution takes, allowing the agents to best respond to these actions, minus the loss of the best fixed action in hindsight had you allowed the agents to best respond. I'd like to pause here for a second. We had a question regarding this in the chat earlier on. If this alpha star exists in the realizable setting, this essentially corresponds to the Stackelberg equilibrium, okay? And how is this different than standard notions of external regret? Well, if you apply the algorithms for external regret in this problem, you would compare against the best fixed action in hindsight if the data did not have agency. So you would take the x hat t of alpha t at their face value, and you wouldn't assume that the people can also best respond to this. So that's the core difference between external regret and Stackelberg regret. Stackelberg regret takes into account how the data can strategize even in hindsight. Okay? And of course, I haven't told you exactly how to define the loss function, and we had another question about that in the chat. Different papers have taken different approaches in the literature. My paper with Yilin Chen and Yang Liu, which appeared in NeurIPS 2020, and the paper by Ahmadi, Behagi, Blum, and Nagita at EST 21 considers binary classification loss. Basically, our algorithms pay a loss of 1 every time that the actual label is different than the predicted label that our classifier gave to the potentially changed data point. But of course, you can have more smooth loss functions. And this was the case in the paper of Dong, Roth, Suchman, Wagner, and Wu at EC18, who were also the first ones to consider this problem as an online learning problem, and they consider logistic and hinge classification losses. What I want you to take from this slide is not so much whether there is a correct or wrong way of defining the losses that you consider. What I'm trying to do here is I'm trying to give you the different models that have been considered in the literature. And then subsequently, I'm gonna give you the results for all these different models. So the first component in how this models differ was what is the loss for the learner that we consider. The second component with respect to how the models differ has to do with how the agents decide to change their features that they report to the learner. So in the paper of Dong et al., the individuals are myopically rational agents. So when they best respond, they maximize their value for passing the classifier, and this value is linear in the classifier, minus a convex cost for manipulation. This is actually very similar to the utility functions that were considered in the offline model. In my paper with Yilin and Yang, we considered agents that were delta-bounded myopically rational. What are delta-bounded myopically rational agents? Delta-bounded myopically rational agents are agents that can misreport in a ball of radius delta, and this delta is known a priori, around their original data point xt. So pictorially, if xt was the data point that was chosen by nature, then and this is like alpha t, the institution's classification algorithm at this point. The point can misreport in a ball of radius delta so that they can pass the classifier. Now, what is important here is that this delta boundedness does not restrict you how exactly you're gonna respond. So you may end up reaching this, the very end of the ball, or you may just like crossing the classifier, or you may end up like not even exerting effort in the correct direction. You may end up just like having an X hat T here. What is the motivation behind that? The motivation is that, if we think about the way that people in practice strategize, we oftentimes see that there's no perfect model that captures their utilities. Instead, what people do is that they oftentimes experiment, and as long as they cross the classifier, as long as they achieve the goal, the classification goal that they had, they just stop strategizing. So delta-bounded myopically rational models try to capture this this uncertainty that we have about how the agents strategize specifically. And then in the paper of Ahmadi, Behagi, Blum, and Nagita, we have again myopically rational agents, but now the value function that they care about is not linear in the classification algorithm, but it's instead binary. So the agent gets 0 if they do not pass the classifier, but they get a value of 1 if they do pass the classifier. And then Ahmadi et al. Consider different cost functions that can be the L1 or the L2 norm. So the question that we try to address in these types of works, in the robustness perspective, is if we take the perspective of the institution, the learner, can we learn to classify strategic agents with diminishing Stackelberg regret? And as a reminder, the two levers that we can pull here are, on the one hand, the loss function that we care for the institution, and on the other, the exact utility, the exact behavioral model that we assume for our agents. Before I delve into the results that we have here, there is a question that I think is interesting and I want to address it. Does optimizing for external regret then converge to Nash equilibrium? This is an excellent question. Yes, optimizing for external regret does converge to Nash equilibrium, but there's a caveat here. As we show in the NeurIPS 2020 paper, there can be cases in general where the Nash equilibrium or external regret and Stackelberg regret are strongly incompatible. This means that if there are settings where if you run any sublinear external regret algorithm, this will deterministically give you linear Stackelberg regret and vice versa. So if you optimized for linear Stackelberg regret, you end up having if you optimize, for sublinear Stackelberg regret, you end up deterministically having linear external regret. And so, of course, there is a big question about when can we avoid that? When can we just like run our favorite external regret algorithm and converge to the Stackelberg optimum? And that we don't know we don't know like any constructive answer to that. So the question that we address here is, if we take the perspective of the institution, how can we safeguard the institution's accuracy if the agents are strategically best responding? And the main results in this area are that, first, from Dong, Roth, Suchman, Wagner, and Wu, we know that when the value functions are linear and the cost functions are convex and positive homogeneous, which means that we have some sort of smoothness, then you can mask the problem as a banded convex optimization and obtain regret that is roughly big O square root D t to the 3/4. And I'd like to remind you here that D is the different features that we have, the set of different features, and T is the horizon over which the setting repeats. So what does that mean? It means that when the world is approximately smooth, we can at least solve the problem with standard toolbox and standard techniques that we know from machine learning. In my NeurIPS 2020 paper, we showed that when the world is not so smooth, but instead we have this like delta-bounded myopically rational agents that there's uncertainty as to where exactly they will end up in this ball. Well, you cannot do this like square root D t to the 3/4. What you can do is a nearly tight regret of square root T log squared T f of delta. And f of delta is a function that depends adaptively on the terms delta, which is the power of manipulation from the agents, and the original data set that nature generated. I'd like to pause here a second and say the following. This is an adaptive bound, data adaptive bound, and it's nearly tight. We have lower and upper bounds about this. Now, why is this important? This is important because it means that in the case that your original data set was quote unquote easy and the individuals did not have big power for misreporting, then you can perform very well. And this is like close to like sublinear in T almost. But in the case that the cards are stacked against you, then you may end up incurring linear cycle regret, and that's the best that you can do. We have a lower bound about this. Now, lastly, I want to discuss the results of Ahmadi et al., which showed that if the data are linearly separable with a margin gamma, this is the standard setting that we usually apply perceptron on, you can change the perceptron algorithm into a strategic perceptron, that's exactly the title of the paper, and obtain regret that scales with the manipulation power of the agents. And of course, it depends, as expected, to the margin that the data had in the beginning when nature provided the data set for the learner. So this was a summary of the results in the robustness perspective in the online learning model. There are many other papers that are usually not from the online learning perspective, but I wanted to try to give you a unified view of how this works basically. So an implicit assumption that I've been making so far is that the population of agents is homogeneous, which means that when the institution decides on a classification or regression rule that is going to make policy decisions, they assume that all the agents have exactly the same power and exactly the same desires in strategizing with their features. But this, of course, is not realistic. If we talk about the loan approvals example, we can, of course, understand that people that belong in groups that are more affluent have had a history of much better credit, which of course impacts their ability to get loans in the future. If we talk about the school admissions example, there are of course kids from disadvantaged populations that have a much harder time paying for tutoring classes or paying for getting the GRE, getting the GRE test multiple times. So it doesn't make much sense for us to be thinking about the population as strictly homogeneous even when we talk about the principle's accuracy. This is the perspective that was pioneered by Hu, Imorlika, Vaughan, and Miller, Dragon, and Hart at FACT 2019. Back then it was called FACT STAR. Why? To give you a pictorial representation of why heterogeneity really matters. Let's think about two subpopulations here in a single dimensional example, where roughly the features of subpopulation 1 are denoted with blue, and the features of subpopulation 2 are denoted in green. And I'm gonna make the assumption that both groups include both qualified and non-qualified individuals. Now, before the best response, let's assume that the learner, the institution, deploys classifier alpha t, which judges both subpopulations as non-qualified, as -1, and no one from the populations as +1. Now, including the manipulation power or the strategizing power from the populations, we can assume that population 1 is more advantaged than population 2. So the manipulation power of population 1 is denoted by delta 1, and the manipulation power of population 2 is denoted by delta 2. So in the example of delta bounded myopically rational agents, a lot of the people from this group, the advantaged group, will be able to jump the classifier, and a few people will be able to jump the threshold and be admitted by the disadvantaged population. This means that if the learner were to run a strategic, off-the-shelf strategic classification algorithm, they would end up identifying this as the Stackelberg equilibrium classifier. And this is rather problematic Because what have we done here? Well, we wanted originally to take into account the strategizing of the whole population, okay? And we wanted to account for that for the learner's accuracy. But in doing so, we ended up making sure that there were qualified folks from some population too that never get the opportunity to get a positive classification from the equilibrium classifier. So in our pursuit for institutional accuracy, we have ended up increasing the barriers for disadvantaged populations. And of course, the summary of this works is that the first punchline was that strategic classification has the potential of disproportionately affecting disadvantaged populations. But even worse than that, there are cases where monetary subsidies make both subpopulations worse off while making the learner better off. So what do I mean by that? I'm going to analyze it in the next slide, but I'd like to briefly overview what we're about to see. We're about to see an example and a case basically for where giving more money to different subpopulations so that we can make sure that they have better strategizing opportunities does help the learner's accuracy, but it makes both subpopulations worse off, both the advantaged and the disadvantaged subpopulation. So we're going to be talking about monetary subsidies. Monetary subsidies means that the institution gives money to make it easier for people to strategize. And we're going to be talking about proportional subsidies. These are subsidies where each group gets multiplicative constant boosts in their manipulation cost. And so I'm gonna play around with a single dimensional feature space. So my classification algorithms, my classification rule will just be thresholds. Imagine that the first group A, the advantaged group, lies somewhere here in terms of features, and the disadvantaged group B, lies somewhere here. So there's some overlap between the two groups in terms of their features. And above this line here, this dotted line, group A, from the advantaged population, people are qualified, they have label +1. And below this line, people are not qualified, so they have a label of -1. And then when it comes to group B, we have that we will make the assumption that above this line here, people are +1, and then below this, they are -1. So the next thing that I want to define is the manipulation power from the different groups. So the advantaged group has this big of a manipulation power, meaning that points that originally started here, they can jump up until here, and then points that started, let's say, here can jump, you can make the transition here. And the manipulation power for group B, which is disadvantaged, is much smaller, okay? So the last points from group B that can jump the threshold essentially are the points on this line, as opposed to the last points being able to jump are on this line. Now assume that the institution's classifier without subsidy is this point here. And this classifier judges all the points that are on the left as -1 and all the points that are on the right as +1. So again, let's think a bit briefly about the manipulation power of the different groups. For group A, all of these agents that are +1, essentially, because it's within their manipulation power, will jump the threshold and be judged as +1. So we make no mistake on these points. And for all the points here, these points, because of the manipulation power, they can jump the threshold. They will be judged as +1, and we will be making a mistake, okay? Because in fact, they are negative examples. So these are the false positives from group A. So this is the only mistake that we make from group A. Now let's look at group B. What happens in group B is that these people are deemed +1 and they don't need to move, so we make no mistake on them. But all of these folks here, they just jump the threshold and they are deemed also as +1. So this means that from group B, we have perfect classification. Okay, let's summarize. What have we seen so far? We've seen two groups, two subpopulations. One is the advantaged, the other one is the disadvantaged. There is some overlap between the two populations. Both populations include plus and minus examples. These are qualified and non-qualified individuals. The advantaged group not only has more space that they cover in terms of their features, but they also have much greater manipulation power. You should think of this as like people that are more rich and they have more ability to spend more money for taking the GRE multiple times or paying for tutoring classes. And then the second group has much, much smaller manipulation power. Now, the institution deploys a classifier that is the Stackelberg equilibrium thing. And basically, this is the classifier that they would have deployed without any subsidies. And what happens when this classifier, this strategic classifier is deployed? We see that the classifier ends up making no mistake in group B. And this is because group B responds to the classifier and ends up jumping the threshold. Points here jump the threshold. But when it comes to group A, we have a couple of individuals. We have some individuals that should be deemed as -1, and they're not. Okay. So what do subsidies do in this case? Subsidies essentially increase the manipulation power of the different groups. So instead of just having this much manipulation power, let's say, for example, that they make you have this much manipulation power. Now, because the learner, the institution, knows that you have increased the manipulation power of the groups, the learner needs to adjust their classifier too. So they have a classifier that is a higher threshold to account for the newly increased manipulation power of the different subgroups. So here's what we have done now. What we have done is we have made sure that all the people from that are +1 from group A can jump the classifier and be judged correctly. All the people that are -1 from group A cannot jump the classifier, so they will be judged also correctly because they will be -1. Now let's see what happens with group B. This small sliver here will be deemed as +1 and they are fine. This group here between the orange and the purple line also can jump the classifier, can jump the threshold after best responding, and they are deemed as +1. But we have this big chunk of space here that is not able to misreport right now, to manipulate. So we have a lot of people that should be deemed as qualified, but they're not. We have false negatives from this group. I'm sorry, this is group B, not group A. So what have I showcased here? I've showcased an example where just by giving subsidies to both groups, and these subsidies are proportional to how disadvantaged, inversely proportional to how disadvantaged they were, we end up having a case where the institution's accuracy can be better off, but it's much, much worse. The situation is much worse for both groups because previously group B was always correctly classified, and group A even had some people that were passing the classifier but are no longer passing. Not only that, but some people, and I think it's also part of the argument in the paper, that false negatives are much worse than false positives, especially the fact that you now have false negatives from the disadvantaged group. So this paints a quite bleak picture, and the insights that the paper has hold for cases where the classification rule is fully revealed to the agents, which means that the threshold classifiers that I mentioned before are announced to the agents a priori. And note that so far, this is the only setting that I've talked about. I've only talked to you about cases where the institution, the learner, comes out, commits to a classifier, commits to an algorithm, and says that, hey, this is what I'm going to be using for the rest of the round or for the whole session. Okay. So I want us to start thinking about what happens when this full revelation principle does not hold. And specifically, I want us to think about what happens when there is some sort of randomness or noise, and whether randomness and noise can improve both fairness and accuracy in these types of settings. This is a question that was studied by Braverman and Garg in their Fork 2020 paper. Although the paper is excellent, I'd like to point out that the results hold for single-dimensional cases, although I do think that you can generalize that for multi-dimensional feature spaces. So how do I even define randomness and noise in strategic classification? So when I talk about randomness, I want to talk about an institution that instead of committing to a single classifier, commits to a distribution of classifiers and picks a classifier from this distribution. This is equivalent to saying that, let's assume a stupid distribution, which has only 2 classifiers, and the bank just tells you that, I'm gonna use this classifier 1 with probability half, and classifier 2 with probability half. And I'm not gonna tell you which one is the classifier that is gonna be realized by this distribution, but I at least tell you that this is the distribution over the classifiers that I'm using. And noise is essentially a way to inject non-determinism as to whether the agents strategize will even help them. This corresponds to the case that intuitively, and this is the example that the authors use in the paper, imagine that you know that in order to obtain a better classification for school admission processes, you have to retake GRE so that you achieve a certain benchmark grade. Now, nobody guarantees to you that deterministically, if you take the GRE 10 times, ultimately you will reach this benchmark. There's always some sort of randomness that masks your ability to do the absolute best response that you should have done, even if you know what this best response is. So roughly, the results of this paper are that when you have the ability to have randomness on your system, then the accuracy increases and the agents are less likely to strategize with their features. And then when there is this noise or non-determinism, fairness increases. And in some cases, you can have even equal classification accuracy to both subpopulations. Now, does that mean that I've solved everything? Why can't we just have random classifiers, distribution over classifiers, or why can't we assume specific versions of noise and non-determinism for the agent strategizing? Now, I think that this is a bigger comment, and maybe you want us to have a bigger discussion around this during the Q&A or during the panel discussion, but I briefly want to say the following. When we talk about randomized classifiers, they are fine in terms of like a theoretical tool that helps us show on pen and paper that accuracy increases. But it's very hard to argue in favor of randomized classifiers when we talk to policymakers about these settings. It's very hard to convince a bank or a credit institution, a credit company, that there should be randomness in the classifiers that they use for loans or whatnot. And of course, there is a whole space in the law literature that deals with sorts of randomness in these types of automated decision-making systems. But yes, the bottom line and what I want you to take away from this slide is that yes, randomness and noise do help address some of the accuracy and fairness problems that we have, but it's still highly unclear how to advocate in favor of that in practice and how it would even look like in practice if we want to do real policy making with these types of problems. I'm going to pause for a second because this concludes the first 2 perspectives. It concludes the robustness and the fairness perspective. And I want to give people the opportunity to ask questions about either one of these 2 perspectives, and then I'll move on to the next one. Okay, I think that there are no questions, but please feel free to ask on the chat if you have any. I'm going to move forward to the improvement perspective. So what have we seen so far? Yes.
Oh, just in case you missed it, there are a bunch of questions in the Rocket chat, but if you've already answered them in the Zoom, that's no worries.
Yeah, we have answered all of them.
Okay, great.
I'm checking the Rocket chat.
Awesome. Okay, thanks.
Oh, there's a new question. Is there any connection to invariance literature defining different environments across which we want to learn invariance? To be quite honest, I'm not sure. I've never thought about this, but I'm happy to chat more afterwards, and I'm happy to get some pointers if you have any, so that I can think more about this. Okay, so what have I done so far? We have defined the robustness perspective, which essentially says that the institution wants to achieve accuracy and suppress gaming from the side of individuals. We have talked about the fairness perspective, which says that, hey, here's what happens when the population that you have is not homogeneous, but instead you have like different subpopulations with different goals, different desires, and different abilities to manipulate and strategize. And now I want to move forward into something that is closer related to recourse and improvement through these settings. And I'd like to bring it back to the very first slide that I had when I was introducing incentive-aware learning to you. I'd like to point out that some of the examples that I had there, examples of strategizing, were not examples of changes of behavior that we want to suppress, but they're examples of behaviors that we want to incentivize people to do more of. If our algorithms can somehow make people improve their credit history before applying for a loan, we want that. If our algorithms for school admissions can make sure that students have a better in-depth understanding of the material, we would want that. And this is what this perspective, the improvement or recourse perspective, wishes to address. Basically, the big question here is, are all strategic changes gaming? So if you think about, if you go online and you Google, what are the ways for you to improve your credit score? Most websites will give you like a variety of different ways that you can do so. You can pay more frequently, pay bills on time, pay back old debts, lower your utilization, increase your credit limit, remove negative entries, and keep unused credit cards open. Now, some of these, of course, are gaming, and it's easier to see which ones are gaming. I mean, some of them are somewhere in the border, but for example, trying to increase your credit limit is I would argue, is a form of strategizing. Or keeping unused credit cards open is also a form of strategizing. Another suggestion that's been thrown around very frequently is for you to increase the number of credit cards or bank accounts that you have. This is also a form of strategizing. But if you end up paying back all of your debts, then this has a causal relationship with how credit worthy you are. Because this essentially means that your ability to pay back future loans has actually increased. So the view of the world that I've been giving you so far in this tutorial is that you have your features and there's a machine learning model, and your features are fed into the prediction that the machine learning model has built, and then this spits out the decision for you. So if we want to think about a standard example in this literature, which is a toy example, if we have a college, let's say Harvard, that wants to admit individuals and decides stupidly that the feature that they're going to base their judgment on is the number of books that people have in their home. And this, by the way, is one of the examples that was originally used in the Hart et al. Paper in ITCS 2016. So of course, in this case, just by changing your features, like buying more books, it's not that you end up changing your true label, whatever this true label is. Let's say for this example that your true label is the GPA that you will be able to achieve if you're admitted to the school. What happens, however, is that in some cases, some of the changes that the model makes the features have end up creating causal changes in the true label. And here's an example. If you take more AP classes in order to increase the probability of being accepted to school, then chances are that you are essentially changing your true label. Okay, there's a causality here that happens. And it seems that so far, we haven't thought about this We haven't thought about this connection here. We haven't thought about how our models incentivize changes in features, and these changes in features actually result in people changing their true labels. Okay, this is distinct from what we saw in the gaming perspective, the robustness perspective, where all we cared about is there is a ground truth, and this ground truth cannot be changed. There's a ground truth label. This cannot be changed. The only thing that you can change is the gaming that you have for you to pass the classifier. And that was all. Okay? So I want us to think about this perspective a little bit more right now. I want us to think about how the models affect the features, and subsequently this affects the true labels that we have. And I would like to point out here that another way of framing this is the question of correlation versus causation. For example, if we have a college that somehow chooses the features that they want to fit their linear regression on before the strategic responses, so they want to be able to use features in order to predict the college GPA of prospective students, this would look like the following. If you used the number of books in the previous example, then probably what it would look like is that, the college GPA doesn't change that much after strategic response. And this is another way of viewing what happens when we have gaming. The ground truth label, which is the college GPA in this case, does not change as a result of you buying and having more books at home. However, if you use the number of AP classes as the feature that you're going to regress on for the college GPA, then even after strategic response, we see great improvement. We see that people's scores become better, students' college GPAs become better. And this is very important because if we are able to show that our algorithms help people improve, then we end up having no cost as a result of our algorithms being transparent. And this is something that we've kind of like hid under the rug so far. So far, what we've been saying is that if the algorithm comes out and announces the classifier that they're going to use, then because this classifier is going to be announced and agents know how to best respond, they're going to best respond and try to fool the algorithm. But here we see an example where you can achieve transparency to no, you can achieve, improvement to no cost of transparency. And this is the point that I want us to focus on for the next couple of slides. I want us to focus on this trade-off between transparency and opacity. And I want to start by asking the question whether transparency is even a realistic assumption in practice. Remember, when we talk about these settings, we don't just care about doing good theory. We also want to make policy change here. So let's think a bit about whether transparency is a realistic assumption in incentive-aware machine learning. So to do that, I would like to revisit the definition of the basic setting. We have a learner, it can be a school. The learner wants to decide the probability of people being successful in college, and they're gonna use a set of features. Now, prospective students, what they're gonna do is they're gonna somehow infer the rule that is known to the agents. This is the standard assumption in the literature, and they can strategically afterwards change their features in order to obtain the best policy for themselves. Okay, this again, like in the school example, you know that Harvard, for example, values you having 100 books at your place, so you go and buy 101 books so that you can pass the classification algorithm. But in reality, institutions rarely reveal their decision rules, and there are many reasons for that. It's not that they are adversarial in how they want to help people, but there are legitimate reasons like privacy concerns, like proprietary software, and so on and so forth. So it seems that there needs to be a study between the trade-off that transparency and accuracy have. Namely, the question that I'm going to address here is the following. Is it always preferable for the purposes of accuracy for the learner's rule to have transparent versus opaque rules? And I'm going to define what opacity and transparency mean in a second. But I'm going to focus on a homogeneous population here. So no fairness considerations. I just care about accuracy. This is by the paper of Galman, Nair, Eilat, Talgam, Cohen, and Rosenfeld from ICML 21. So the question that I want to address is, how should the institution choose between full transparency and opacity in the decision-making rule? Full transparency means that the institution comes out and says, hey, this is exactly the model that I'm using, this is the linear regression, this is the algorithm that I'm using. And opacity means that basically the institution does not allow the agents to see the full rule. And opacity has been modeled in different ways. For example, agents may have like sampled access to the decision-making rule. I believe that this is the case in this example, in this paper too. So let me denote by orange F a transparent rule, and F hat an approximate rule that the agents infer. Okay, this F hat can be from like sample access to F. Now the authors of this paper define the price of opacity. The price of opacity is the difference between the error obtained under F hat after the agent strategized. So this is the error, the accuracy error for the institution under the approximate rule that the agents infer after they strategically best respond to it, minus the error that the institution, incurs under F after strategizing. So in both of these cases, we compare the case where the agents will best respond to our rule. And the difference between the two cases is that in one case, the case of the HAP, the rule is only inferred by the agents, by sample access or whatnot. And then in the other case, the rule is fully revealed to the agents. And of course, if we have a price of opacity that's positive, then opacity is not preferred over full transparency. So I don't know about you, but when I was thinking about these questions, my expectation was that if the approximate rule that the agents infer is very close to the actual rule, which is what the learner uses, then we should be able to obtain similar punchlines from fully transparent strategic classification. We should be able to have similar guarantees, and not only that, we should be able to say that opacity helps. It should be able for us to argue that when you mask things, it's only better for you. Well, surprisingly, and this is what this wonderful paper shows, sometimes for linear classifiers, opacity can hurt the institution's accuracy. And the paper provides specific sufficient conditions for it to be the case. But I would like to give you some intuition as to why this is the case in the first place. So first of all, this paper assumes that the form of F hat is not known. So this means that the institution does not know a priori what exactly is the algorithm that the agents use in order to infer F hat. This means that the agents may end up being incentivized to modify their features very differently under the original rule F and the rule F hat. If F hat, however, was anticipated, then we can basically achieve similar results to standard strategic classification. So what have we seen? We've seen a case where full transparency is actually not preferred to opacity when it comes to the accuracy of the classifier. Okay, and this is the case with a homogeneous population. So we talk about a robustness perspective here. I want us to switch gears finally and think about the fairness implications of non-transparency. So instead of thinking about a single group of students now, I want to talk about two groups. One is the advantaged population in blue, as we had previously, and the other one is the disadvantaged population in green, as we also had previously. And what am I going to assume now is that these populations do not have direct access to the decision-making rule. What happens instead is that each of the subpopulations has access to a peer network of sampled points based on which they build different models for the classification rule. And based on this inferred rule, they know how to strategically change their features. So I'd like to instantiate this with an example. Think about the standard college admissions that we've been talking about throughout this tutorial. And let's say that subpopulation blue, the advantaged subpopulation, comes from a very affluent neighborhood. And subpopulation, the green subpopulation comes from a very poor neighborhood. Now, kids from these two populations may go to different tutoring schools. And each of the tutoring schools has a set of examples from previous applicants that have applied to the colleges that these students want to apply. And so they have their own kind of like sample access to the decision-making rule. Note, however, that the sample access is very biased based on the samples that each of the tutoring schools has. So tutoring school blue has mostly access to students that come from this very affluent neighborhood. And of course, the tutoring school green has access to the mostly poor students. And when they build their estimates of the world through, let's say, running a NeurIPS process, this ends up causing very disparate impacts in the way that the two subpopulations of students strategize with respect to their college admissions. Another way to say this is to say that basically what each of the agents understands for what matters for the school is for the college is very, very different. So the question that we addressed in our ICML 22 paper with Yahav Bekavod, Stephen Hu, and Jubaziani was, if the learner is a benevolent agent and maximizes the social welfare of the total population, how does information discrepancy affect the subpopulation's ability to improve? Again, what are we trying to do here? We're saying that if the learner not only doesn't care about accuracy, but actually wants to help the subpopulations improve as much as possible with respect to their social welfare. How does this difference, this discrepancy between the information that the subpopulations get affects how much their social welfare gets to improve? And very briefly, I'll just tell you that our results, which are both theoretical and experimental, we show that sadly, the disadvantaged population may end up being strictly worse off when participating in this setup. So not only is there no improvement, but the population becomes actually worse off as a result of this. And not everything is terrible, thankfully. There are some cases where at least each of the subpopulations can achieve their optimal outcome, can achieve the optimal improvement that they would have been able to achieve if the information for the two subpopulations is kind of independent. And I know I'm defining this loosely, but basically the intuition behind this is that the movement of each of the populations does not negatively affect the movement by other subpopulations. That's why we want the independence in the information that the populations have. And with that, this concludes the improvement perspective for this tutorial. And I would like to pause and get some questions. And then if there are no more questions, I will move forward to the open directions in this area. But I'll wait a minute in case people have questions in the chat. There's a question. Meta-observation and agents causally changing the features, the true features. Could this perspective explain controversial policies like affirmative action or its luck? Unfair in EO terms today, but induces agents changing true labels in the long run in an optimal way? Good question. So let me try to abstract away from this question and try to place it in a more mathematical perspective. Based on the work that I talked briefly about in the ICML 2022 paper, this basically says that you do need policies like affirmative action so that you can transmit more information to the disadvantaged groups. Because if you do not do that, then you end up having these terrible fairness guarantees. But I think that so far as I can tell, this has not been made concrete in the literature so far. And it would be very interesting, actually, to make the case for affirmative action using the causality framework in incentive-aware machine learning. But I would like to point out here that something that's really hard in this area, and you don't point out to this exactly, but I wanted to bring it up, is that how do we even define gaming and improvement? Like, in some cases, it's like clear cut, I agree. but it's not always. And I also don't believe that this is a question for us as like technical people to address all by ourselves. Like there are tens of years of research in like sociology and social sciences that think about, what types of incentivized behavior, what types of behavior should be incentivized and what types of behavior should not be incentivized. And so I think that addressing these questions does not just come from our community. It requires people from other communities too. That was a very good question. Okay, let me briefly, in the time remaining, go over the open directions that I can summarize from this tutorial. So the first theme is for open directions from the side of the institution. I've mostly talked about linear rules in this tutorial. I think that I only talked about linear rules. But in reality, real life machine learning systems are very, very complex. And of course, I have a background in theory, so understanding first what happens with linear rules is the first kind of like point of contact. But if we really want to have this area drive policy change, we need to start thinking about nonlinear rules coming from neural nets, from like very, very big systems. And when it comes to these complex machine learning systems, I think it would be more clear to model questions on trade-offs between transparency, accuracy, and noise. The second thing that I think should be what we should be thinking about in this area is what are the actual behavioral models that the agents use. So it may be the case that agents are even using machine learning algorithms themselves. I know that when we talk about like the school admissions example, of course, parents are not machine learning algorithms themselves, but it may be the case that websites that are helping you change your features for a loan application are using essentially some machine learning algorithms. Also, it's unclear what happens when agents do not exactly best respond, but they approximately best respond. And of course, we had this like one paper at NeurIPS 2020, but that was very specific. That was for linear rules, and even the approximate best response of the agents was kind of structured. And then I want to understand, I think it's important for all of us to understand what happens when our models for human behavior interpolate between fully strategic and fully adversarial. So this has to do with a notion that has appeared recently also in economics, and it's about the sophistication of the agents that you face. Do we really think that everyone has the same ability to understand the rules and respond to them? Do we even believe that all of our agents are strategic? What if some of them are strategic, some others are not sophisticated at all, and then we have some that just want to completely destroy the system? And the third theme, which I alluded to, especially in the later parts of the presentation today, has to do with policy. And how do we transition from a theoretical level of research to a level that does actual policy and like deploys these algorithms in practice to make consequential decisions? And again, this is my viewpoint of what I think the direction should be. I'm happy to discuss more during the Q&A or the panel. But I think that one thing that we need to do as a community is we need to stop coming up with utility models that make sense to us and essentially start running experiments to understand, but to obtain a better understanding of how the agents actually strategize in real life. These experiments can be contrived to Turk or even big field experiments. I think that by building such large case studies, this is the only way to be able to apply these insights of this research agenda to make policy change. And with that, I would like to thank you all for being a wonderful audience today.